Good morning. Good morning, everyone, and welcome to today's webinar by Radiocrafts. Hope you're all having a very pleasant morning. Hope you have your coffees ready because today we have a very interesting topic to speak about. A topic that has certainly been asked a lot in our customer support email. We often get much inquiries from customers asking about this. So I have a feeling this will be great and it'll be very informative and to really help many of our customers with the questions they often encounter. So please let me welcome you this morning and thank you for taking the time for joining us. If you just joined, please feel free to introduce yourself in the chat window. I'm just also waiting for more people to join. Meanwhile, you can pour yourself some coffee and get ready. All right, so my name is Omar. I'm an applications engineer at Radiocrafts, but also this webinar is the brainchild of Ørjan, our R&D Director at Radiocrafts. We thought that this would be a very good idea to clear some of the questions which we get asked a lot. So we will try to have this webinar. It's very informative, but we'll try to keep it at 30 minutes, and we will also try to have a 15 minutes Q&A session at the end. So while I'm speaking, please feel free to write your questions in the chat window, and we will do our best to answer them all after the webinar is after the presentation is over. And of course, as usual, we will post a recorded version of the webinar on our website in case you want to go back to it and listen to it again. And this will also be accompanied by a very detailed application note, which will be out soon, which of course will have way more details than we can put in a presentation. So I guess now everyone is here, everyone is ready, so let's go. So what are we going to speak about today? Today we will discuss about how to design your RIIM network and what kind of parameters you have to think about and what kind of parameters you can tweak and what you can't tweak. We'll also discuss what you can expect from your RIIM network. So first we'll start by the parameters and what parameters are important for your application. And then we will discuss RIIM and options you have with RIIM, either single channel or TISH. And then some of the nuts and bolts which you can tweak and play with to change the performance of the network to suit your use case. And at the end, for the most interesting part, we have some simulations results and design guidelines on how to set your RIIM network for the best performance according to your specific use case. And for the people listening to us for the first time today, I want to just briefly speak about RIIM. RIIM is Radiocrafts IP Mesh network. It has end-to-end IP packets. It has a border router, mesh routers, and leaf nodes. It also supports cloud connection. It supports the single channel and TISH modes. And the main focus of today's presentation will be about TISH. All right. So how can RIIM help you? What can RIIM do for you? What do you expect to get by using RIIM? Do you want to cover a very large area? Do you want to deploy have a mass deployment and have a high number of devices in the field? Do you need very low latency for near real-time applications? Maybe you also need many years of battery lifetime. How big the messages? Do you want them more than 50? Do you want ultra reliability and ultra availability? I want to send uplink messages every 30 seconds. Maybe you want your network to be formed very quickly. Well, as just everything in life, nothing is perfect, and you can't have everything at the same time, especially in RF, because always every parameter is built upon sacrificing another parameter. So if you want very large number of devices, then you can't have the very low latency, but maybe you can have higher network formation time, but then you will have good throughput. So everything has to be balanced and everything has to be optimized for your own use case. So what can you choose in RIIM? What are the options that you can actually choose from? Well, first you have RIIM, then you have single channel mode, which just makes you select one RF channel and you operate on that. But then on the other side, now you also have TISH. What options do you have with TISH? Is it only one thing? No, it's actually can be roughly divided into two modes. Passive mode or receiver based, and active or sender based. And that's not it. Also in passive mode, you have three options. You have the low power mode, the balanced mode, and the high throughput mode. So in RIIM in general, you have TISH on the right hand side and then single channel. With single channel, you only get to choose one RF channel, but then with TISH, you have two modes you can operate on, either passive or active. That's not only it. In passive, you also have three other settings to choose from. Okay, but how do these settings work and what can you do with them and what can you expect from them? That's what we'll see now. First, we can touch on very briefly with the single channel operation, the one which was on the left. Gives you the most battery efficient leaf nodes. They have an average current consumption of 4.7 microamps. Of course, leaf nodes can go to sleep. You can program them via EC to wake up at certain times to send uplink packets. But of course, a leaf node is not a mesh router, so it cannot route data up and down the network. And of course, they cannot receive downlink at any time because they're usually at sleep. So they have to, upon wake up, they have to pull their parent node. So that's how single channel works. It supports leaf nodes, which have very low power consumption, and they can, of course, go to sleep. But of course, the problem with that is that leaf nodes do not route data up and down. That's why you also need battery operated mesh routers, and that's what we did with TISH. So what is TISH? What do we do with it? Now TISH in general, without going into details of passive and active, just on the very high level. In TISH, the airtime is divided into continuously repeated set of time slots. Each of these time slots is 40 milliseconds. So the airtime is divided into 40 milliseconds, then 40, then 40, then 40. And of course, the radio does not have to be on all the time. And that's how we enable battery operated mesh routers. And of course, this means that the mesh routers can go to sleep most of the time, and they only wake up when they want to send or receive data packets. And of course, this supports channel hopping. So as we said, this allows for the battery-operated mesh routers. It allows for, by using TISH, you can use polite spectrum access techniques such as adaptive frequency agility and listen before talk. These kinds of techniques, they allow for using higher duty cycles under European regulations. Of course, this gives you higher reliability since it uses channel hopping. It allows also for time synchronization. You can now have, using RIIM, you can have time synchronized actions on your network and events. And of course, some regulations require channel hopping. Sometimes that's not even an option. So TISH is good for that. And of course, it mitigates noise and it mitigates jamming since it uses channel hopping. So these are the advantages of TISH on a very high level. Now, if we dive into a bit more detail, we can speak first about the TISH active mode, which we call the sender-based. So sender-based or active, it's the same. Why is it called sender-based? Because using a special algorithm, the node calculates the time slots where their neighbor is allowed to send. So a node calculates what's the time slot that its neighbor is allowed to send, and then it turns on its radio to expect a packet from it. And of course, in all other times, the node is asleep. In the TISH category, active mode consumes the most battery. Of course, that's still less than single channel, but in TISH, relative to other TISH modes, active mode consumes the most battery, but also provides the most network performance. And this is just very briefly an example of how TISH active or sender-based mode works. You can see on the left-hand side, you have node A and node B. So node A says that, yeah, it knows that node B sends every, let's say, for example, 7th time slot. So node A will be always asleep, but it will turn its radio on only at time slot number 7, where it knows that node B might be sending information. On the right-hand side, you can see very briefly how the time slots work. It's 40 millisecond, 40 millisecond. At the first 40 millisecond, which is listening window 1, maybe nothing happens, and that's, of course, just an example. In the second window on the right, we can see that node B is sending to node A. So node A will open first its radio for 3.5 milliseconds. If there is, like in listening window 1, if there is no transmission, it will turn off its radio again. If there is a transmission, it will keep the radio on and it will receive from node B, then it will send an acknowledgement. That's very briefly how sender-based works. Now, the other type, which is passive, or what we call receiver-based, the only difference is that now nodes calculate the time slots when their neighbor is listening. Then nodes send the packets in that time slot. So it's the opposite of sender-based. And of course, relative to other TISH modes, passive mode consumes the least battery, but also provides the least throughput. And of course, this is optimized for applications when you care more about battery lifetime than you care about throughput. And very briefly, this is how it works. You have node A and node B on the left. Node B wants to send to node A. So node B says that I know that node A listens every 4th time slot. And you can ask me, how does it know? Well, that's because using TISH, there is a common understanding of time using special algorithms for all the nodes. So all the nodes, they know information about each other, which is sent in the network maintenance packets. So node B knows that I know that node A listens every, for example, 4th time slot. Then node B will say, okay, I'll send my data in that 4th time slot because that's when I know node A is listening. And on the right-hand side, we have the same example. You can see that, for example, node B, this is listening window 1 is the time slot where it should be listening. It opens the radio, turns on the radio, nothing for 3.5 milliseconds, goes down again. But then in the second time slot, there is actually something, so it keeps it on, and node A now can receive the packets from node B and then send also an acknowledgement. So this is just the basic idea, very simply about how TISH works in active mode and passive mode, and how actually TISH enables battery-operated mesh routers. It's by allowing mesh routers to go to sleep in between transmissions, and they only wake up at certain times. Okay, so that was TISH. Then what can you do as a user? How can you tweak RIIM to get the best performance for your own network? Well, there are many things you can play with. You have reliability. How much do you want of that? You have latency. Do you want it high? Do you want it low? You have battery lifetime. You have the network formation time. You can play with all this. And this, of course, depends on how dense your network is. Do you send sensor data only to board the router or to a terminal or to the cloud? Are you controlling devices in the field, or are they only sending uplink messages to the controller? All these things you can control and play with to change the network's performance. Okay, so what can be done? Well, there are some things which we did for you to make it easier, because going into the details of TISH and really tweaking every single parameter is not that easy. So we did some things. We created this active mode, we created the passive mode, and then in passive mode, we created 3 settings, which is high performance, balance, and low power. And how they differ is that we changed how often nodes turn the radios on. We changed how often there is a time slot. Like if time is divided into 7 time slots, for example, then the 7 repeat, then you would have much time slots. Like let's say node A can send every 4th, and they're all 7. So it will be 7. And then in the next 7, number 4, node B can send. Next 7, number 4, and time slot 4, node B can send. But if we make it 25, for example, then you have to wait 25 time slots till node B's turn comes again. So these are the kind of things we changed. We also can change the time slots dedicated for beacons. So also how often the beacon is sent and how often nodes listen to that beacon for the network formation and for network maintenance. These are the kind of things we changed and tweaked to give you these 3 settings: high performance, balanced, and low power. And these settings are only in passive mode. So you have active mode, which consumes the most power and gives you the most performance. And then you have passive with its 3 sub-modes. Then there are also some tweaks which you can do yourself. You can choose first one of these above one of these settings. Then you can also change the beacon broadcast rate. The beacon broadcast rate will affect the network formation time. Is it here? Yes. So what is the beacon broadcast rate, which you can change? It's just an announcement of the network. So basically, when you first start your network in the joining phase, which is the network formation phase, the announcement, the beacon is important because it tells the nodes about the network and how to join it and what power to use and everything. And then when the network is formed, after some time, you don't really need much of these beacons. So what you can do also, a very nice trick, is that you can first start the network with very frequent beacons to allow all your nodes to join very quickly. And then through C code in our AC application, you can set a function which then causes this beacon to be more delayed and slower and slower and slower as the network goes on. Since after all nodes join, after 1 hour, 2 hours, 3 hours, you will not really need that much frequent beacons for all the months or years that your network will run. A good thing to know is that the 3 modes which we did, which are the low power, the high performance, and the balance, they determine how often these time slots for beacons occur. But what you can change is this command called set tish max broadcast rate. You can actually determine how often these beacons are used. So that you can do, and of course, the more you use the beacons, the faster the network formation will be. But of course, the more battery will be consumed because nodes have to send and listen to these beacons. A very good trick that you can also do is having a join button. Let's say, for example, you have a network with 20 nodes and you started it and they joined, and then you did this, let's call it dynamic or adaptive beacon rate, that at the beginning of the network, the beacons were very frequent, so all nodes joined very quickly, and then it became slower and slower and slower. Then let's say after a year, you want to add 1 more node. So you go, you buy it, and then you install it. It will take very long time to join since now your network has been running for a year and the broadcast rate is very slow. What we can do is that you can have a button, for example, on the border router, which when you press it, it calls a function which then makes the broadcast very frequent again. So it will allow that new node to join, then it will be slow again. So there are always many things which you can play with. And then you also have the robustness factor. This refers to the very simple idea that you can control the least RSSI which a node can accept a neighbor on. Let's say, for example, minus 85 dBm. And you can tell a node that any neighbor you have which is under that, just don't accept it. And of course, this will give you more reliability and more packet delivery rate, and it will avoid lost packets due to bad connections. Okay, so I don't want to take you more into the theory. I want you also to be to listen to that interesting part about the simulation results and actually how the numbers go and what you can expect from your network and how real networks in real life situations work. So I would like now to welcome Ørjan, our R&D Director, who did you really very interesting simulations, and he will now present you these simulation results. So good morning, Ørjan, and the mic is yours.
Thank you very much, Omar. So, as Omar pointed out, there is many different settings you can tune on, and they will be different for different use cases. So I'm going to go through a couple of use cases here, which we have seen used a lot, and how these parameter tuning can affect that. So the first use case I'm going to talk about is battery operated mesh. So that is often seen in smart agriculture. We have seen it in smart irrigation. We've seen it at construction sites, mining, sports. You can have it in structure monitoring, predictive maintenance. So the common here is that there's no power infrastructure available. So that means you want to cover a big area. You want to send maybe both sensor data and control data down, but you have to kind of place out the whole network. So, 1 second here. Oh, sorry. Sorry for that. Yes. So how do we kind of calculate the battery power consumption? Because that's kind of the key performance criteria for most of these networks. So that's kind of how long will the battery last. So typically you have all mesh routers will have a base current consumption of about 100 microamps. And then it also will be affected by other elements. So for instance, it will be affected by the number of neighbors. Why? Because if there is a neighbor node close to you, you need to have some sort of time slot available to communicate to this specific neighbor. So that means you will listen once every second, 2 seconds, whatever, on that specific node to see, does that have anything to send to me? Because if you want to have a mesh network which is reliable, each node must have different path to send the same packet. So it must have different options. And that means that all nodes must listen to the neighbors. So we have simulated this and see that a neighbor node, typically what we have seen, this simulation is based on passive mode, as teach passion mode, as Omar explained, and it's based on using the low power settings there. We see that the neighbor increases the current consumption approximately by 0.8 microamps. So 0 neighbors is the best, but then you don't have any robustness in the network to have multiple paths to send your own packets, so it will reduce reliability. So that's why number of neighbors is important to have reliability. But if you have 100 neighbors, 100 other nodes you can listen to, you probably have a very dense network, and it doesn't really, the 100th node doesn't really give you any reliability. Then you have the number of children. Why is the number of children important? That has to do with the fact that if your children, you can imagine your mesh network as a tree structure. So that means if there is somebody below you in the tree, that means any data traffic they want to send to the board router, you also have to send the same packet. So that's why it's increased by that. Capacity settings has to do with this low power balanced and high performance settings that you can do, which basically tells the frequency hopping algorithm in TISH how often it should listen. So if it listens once every 10 seconds, obviously you can send very little data through that node because it listens only once every 10 seconds. But then it will, of course, be very nice from the current consumption point of view. And also exactly how much data this node generates will also affect this. So all these things will affect. And that means that it's very hard to say exactly how much power consumption one node will use. But we are working now, as part of this presentation, we're also working on a new calculator, which will be an estimating calculator where you can put in your settings and then get an estimation of the power consumption. So that will be shared on our GitHub account when that is available. So, as I said, part of this power consumption is driven by the capacity you set up on the network. So here we have different settings. So these, what you see at the bottom of your screen is, or at the x-axis, is different settings. So at the right side, you will see this ultimate current consumption setup where we have less than 100 microamp of current consumption. And then you can see that by adding more time slots and going to this balanced and high performance mode, you see the current consumption goes up in terms of microamps, but you will also have higher capacity in your network. Also, we talked about traffic, how much sending a packet from your application to, for instance, the board router will affect your current consumption. This is also based on the simulations we have done on this network, and we see that if you send one 4-byte packet once every minute, that will increase the current consumption approximately by 5 or 3 or 4 microamps. So that's not a lot. But if you have many children and they all send packets, you have to send it. You certainly have to send a lot more packets. And you'll see also that if you send 30 bytes and 60 bytes, that will make the current consumption increase more rapidly. So reducing the amount of data you want to send is obviously a good thing. This can just be extrapolated to the right to see if you start to send packets every seconds, for instance, from a node. That's obviously not good for power consumption. So what do you end up with? How long will your battery last? This is 3 different scenarios in the 3 different columns, and we have 5 different battery sizes. So this is how many days your battery will last, and this estimation is based on using 90% of the battery capacity. So not 100% of. You can hardly ever use 100% of a battery capacity. So this is based on 90% of the battery capacity. And we see that on the first column, you see that if a node doesn't have any children, it only has one node it's talking to, which is maybe the board router. So that this is a very simple case. We use TISH passive and low power as the settings. We use a max broadcast rate when we are after formation, but so network is formed, we're going into static phase. We use max broadcast of 64. And then we send 60 bytes every 30 minutes. So that will lead to half AA battery will last for approximately 379 days, which is more than 1 year. And one AA battery will last for more than 2 years, maybe 2.5. So then we see that when you have, for instance, 4 children, so basically the settings are more or less the same, but that means you don't only send your own packet every 30 minutes, you also forward your children's messages every 30 minutes. So the traffic is kind of 5 times as much as it was in the first case. And you also have to just listening to all your children's time slots. So this makes it the lifetime a bit shorter. Sorry, but more like is it 5, 6, 7% shorter than the original one. And then we can see also by adding even more nodes. So on the right column, you have 12 different nodes, all sending data through the one node we're investigating. And you see the current consumption is also, or a battery lifetime, also goes slightly more down. So based on the new calculator that we will make available, you will be able to do your own cases as well. So that was the battery lifetime. So that's based on customers who need that type of network. Then we have other type of networks. So one other is more. This is also a typical use case. We have 32 nodes in a building basement, typically with EV chargers. So this is typically a mains power network, and reliability and latency is key elements much more than battery lifetime. So this is how the network we simulated on looks like. We have 32 nodes. Around the black nodes, we have a big circle showing the range. So there's so obviously not all nodes can listen to all nodes here, so that's why we need the mesh. We can have up to 4 hops in this network, as we have seen in the simulation. So here we see focused on uplink traffics first. So that means we have sent data from the different nodes, a bit randomized in time. And then we have seen how much data can get up through the board router. So in the TISH active mode, where we also used the high performance settings, we have seen that we can send up to approximately 4 packets per second in average, and still have a packet delivery rate of close to 100%. If we should use the low power mode, for this, we see that the capacity is much less. So we see that if you start to send 1 packet per second to the board router, you will also, at that point, already lose like almost 2 out of 10 packets. So choosing a low power mode will affect the capacity at uplink. However, if you look at it downlink, you see that the passive one will actually give higher capacity. So the passive mode is, the passive mode of TISH is very good for sending control data down. And I think that's one of the key elements of the passive TISH. You see here, you can send, again, it crashes a bit after 4 to 5 packets. Then it's up to 10. You cannot, you start to lose a lot of packets. But sending 1 per second from the board router is fine. And probably with the TISH passive, you can actually, you could send 3 or 4 or 5 packets per second. Yeah. If you also look at uplink again, latency is also a key here. And obviously, having this TISH active mode gives you much lower latency. This is an average latency in the whole system, and it is so some of these nodes have 1 hop, some have 2 hops, and some have 3 hops to the board router. So it's not for 1 hop, but this is for the whole end-to-end. You see with the TISH active, we see that the average latency is approximately half a second. While if you go to the TISH passive mode, which is meant to save power, you see the latency is approximately 2 seconds, and it starts to increase also earlier when you increase the packet rate. So again, conclusion for this is that you have to look at how your traffic pattern look like. Are you sending data up mostly, or are you sending packet down mostly? Also, a key design point, or in our kind of design guidelines, is to spread the data traffic. So imagine that all nodes want to send their status at 12 o'clock, and you have 500 nodes in your network. Obviously, that will create a congestion at the time when you send it. We had other use cases where customers wanted using Streetlight, and customers wanted to send an alarm if they lose mains powered on each lamp. Okay, that sounds nice, but you also have to consider, well, typically the power goes on all lights at the same time. And if you have 100 lights and they all want to send this packet at the same second, actually, that will create a short-term congestion in the network, and you will lose some of the packets. So how can you avoid these type of congestions, which are at specific times? Well, one thing you can do is use randomization in your EC code. So you don't send every 5 minutes, but you send every 5 minutes plus minus a random 20 seconds. This will move them around. So that will statistically give you a nice distribution over time. Other way is to do polling. That means that if you want to send some regular data, that means you could, instead of sending regular data, you could have your board router send a read message to each device to poll some data. This will make sure that there's only one message in the network at the same time, so that will give superb reliability. However, you will then not use the full capacity of the network, so you will kind of slow down a bit to make sure that you have full control. So I see we have used up slightly more than 30 minutes. So the summary of this is that RIIM offers many benefits. So it has low power, it has low latency, it has good throughput, it has cover long ranges. So it offers a lot of benefits, but you have to choose which is important in your specific use case. And it is important then to set up your network correctly for that given use case. So if the battery consumption is critical for you, you have to use TISH. If you need battery operated mesh routers, you need to use TISH. Frequency hopping, you need to use the low power variant, which is a passive mode. And then you have to also make sure that you set the beacon rate dynamically. So that means that after the network is formed, you slow down this announcement of the network, because otherwise nodes will just be wasting their batteries screaming. And then you have to also, specifically in high traffic networks, you have to make sure to distribute your traffic uniformly, so that you can don't get local congestions in certain times if all nodes happen to send at the same time. Okay, then I will say thank you for listening, and we will look at the chat to look at the questions.
Maybe Ørjan, you want to catch your breath, and I can take like the last two questions, then you can take the rest.
Yeah.
All right. So regarding the question of Magnus about the current consumption and leaf nodes, the thing is, TISH does not have leaf nodes, because the good thing about leaf nodes in single channel is that leaf nodes can go to sleep. But then in TISH, also mesh routers can go to sleep. And of course, they can route data up and down. So that makes leaf nodes not, they have no use anymore. So that's why there are no leaf nodes in TISH. And you also see that in the platforms you get in the SDK, there is no TISH platform for leaf nodes. Then there was a question by Elmark Petroza about how RIIM compares with the Bluetooth mesh. I think the main thing here is that Bluetooth mesh operates on the ISM 2.4 gigahertz, but RIIM is sub 1 gigahertz. Of course, that gives a very different profile when it comes to range, when it comes to connectivity, when it comes to how many nodes you need and how much power you will consume. Of course, with RIIM is made just as an IP mesh network, so you get all the other benefits that you're getting with TISH, like time synchronization, like polite spectrum access techniques, like getting higher duty cycles, like you have also with the mesh with the TISH, RIIM, you have the high power. Yes, the main thing with the Bluetooth is that it's in 2.4, and I think that's very critical when it comes to range. According to, I think their official numbers, it's like 10 to 15 meters indoor and some few hundreds outdoors.
Also, Omar, I can add in that one of the differences with BLE Mesh is, of course, that they don't route the packet downward. So as far as I understand, the BLE Mesh uses flooding. So if you have 30 nodes, you have to use flooding as a technique to send packets to one node. You have to send to all. So that means a network packet will then use quite a bit of time in the network to make sure that it has traversed to all nodes before you start. So in RIIM, we send routing to a specific node. So that means that it's only sent directly to that node. So that's a key difference. Okay. Also, there was, let's just see, if we start at the beginning, how would you compare yourself with other mesh like SignCanode and WirePass? The key difference between us and for instance, WirePass is I believe that WirePass is a 2.4 GHz solution, as I see it today, and that means they obviously have at 2.4 GHz you have shorter range, but you get also shorter, higher data rate, and you get shorter packets. So I guess WirePass is much more comparable to BLE mesh. They work basically on the same hardware. So in terms of range, they are the same. So SignCanode, I don't know that much about, to be honest. So I haven't seen it for some. It's been some while since I looked into that. And RIIM and timestamping is also some questions about, which is yes, in RIIM we have a time. We have a synchronized network, so all the nodes are synchronized within basically less than 1 millisecond. Less than 1 millisecond. So that is obviously good for having control of time. However, if you're looking at time of arrival in terms of location of a packet by time of arrival, we don't have that support. In terms of RIIM and localization, I typically see, I think I see more RIIM as the backbone, and then using RIIM in combination, for instance, with BLE, so that you have many BLE devices, and then using RIIM as a backbone to send data through these to these if you use them as to this BLE locations time. So it's more in that context that it is it's useful. How do you compare your tiny mesh based solution with other RF technologies like SignCanode and WirePass? The tiny mesh is a different mesh technology from that offered by Radiocrafts, which is a bit more mature and simpler mesh structure, and I mean, it's a bit difficult again to compare it to SignCanode. SignCanode, I believe this is a centralized system where a lot of the intelligence is in the board router, which controls the whole network. And again, WirePass is like a 2.4 GHz solution. It says something about payload size here. Can we send 300 bytes in a single shot, or do the application need to partition into smaller chunks, or better, the RIIM stack handles the partitioning? The RIIM stack handles the partitioning of the packets. But then also know that, for instance, on the UART input, there is a maximum length of 255. So that means you cannot get more than 255 in one UART packet into the module if you have it externally. But the module does the partitioning and divide it in different chunks, and obviously sending 300 bytes will divide it into more than one packets, because we are basing ourselves on 802.15.4G, which is and 128 byte packet length in total. So typically 100 microamp current for routers only. Is the leaf still? Yeah, that I guess is already covered. That means that a leaf node still, as Omar said, the leaf node doesn't really exist in TISH, and the 100 microamps is for the lowest power consumption nodes in TISH. So if you really want this 4.7 microamp current consumption, then you have to use to get that, the device sleeps for minutes, hours, if you want to. And that means that the router must always be on, because if you have certain time slots between the leaf node and the mesh router, then you need to then the leaf node needs to wake up maybe every second, and obviously that will create current consumption. Was there more questions I missed here? Is 100 micro the current you can get? Let's say, is 100 microamp the smallest current consumption we can count on? Battery lifetime of a few years with 2.6. I guess we answered that. I think yes, if you want to go to like 2 or 3 or 4 microamps, then you need to use leaf nodes, and that means you're basically using single channel operations. Max payload is 128 bytes on the physical level. So that means that your application will have fewer bytes on that. It will actually vary a bit depending on if you use co-op, for instance, and it has more overhead than both co-op and DTLS will give you overhead. So that means you have actually fewer bytes than for your application. But you don't have to consider that when you do the application software, because the stack will handle and fragment any packet which is too big into smaller packets and send them one by one. I also have to say on the BLE mesh, as far as I understand, the BLE mesh does not support sleeping routers or mesh routers which are battery operated. But that's, I guess, an important difference as well. So I think we have covered all the questions now. So thank you very much for listening in, and we hope you enjoyed this presentation, and have a nice day. Goodbye.